don't turn up. Most times, it's just, especially 9:30 a.m. classes, they're miserable. And for some reason, people turn up in January when it's really horrible. By April, when it's nice and warm and spring outside, nobody wants to come. What's this? So can you hear me on the mic?
You're good. Yes.
Perfect. So, all right, how many of you have actually managed to submit most of your homework? Okay, good. First, don't get too panicky about whatever performance that you've got. Remember, this is one of many homeworks, right? We have 4 coding homeworks. Your 5th homework, which was originally supposed to be coding, is now we figured we don't want to overburden you, so it's just going to be a midterm report for your project. So you have 4 8 half homeworks, quizzes, a midterm report, and your project, final project, all of which to score marks with, which means that you shouldn't be panicking about getting 2 points less in the first half of the first homework, right? Second, the point of the homework was A. Yes, B, we found people get overcompetitive. These homeworks are meant to be for you to work on, not your friends to work on for you, right? And there has been a certain amount of, how shall I say, distributed computing going on, because people got competitive. They got together with their friends. Everybody ran a different experiment. I mean, perfectly valid. I'm not disagreeing with the principle of it, but the idea was this was supposed to be you doing it, not your friends. But the idea that you're exploring all of these options is a good thing. Again, the point of the first homework was not so much that you beat your classmates. It wasn't about you competing with each other. It was about you competing with the baseline. That was important. Now, on this particular data set that we gave you, the typical performance that we get is about 65%, 64 to 65%. And we found that you guys, some of you managed to squeeze out 67, 68, close to 69%. And I think if we actually take the top few results and combine them, it will probably go above 70 or even higher, right? So we're looking at some results which are beyond what have actually been reported by most groups who work on the same task, unless they've spent a lifetime tuning performance on it, right? So you guys are pretty good. Those of you who managed to get all the way to the top are pretty close to where you should be on that task with not a whole lot of effort. And the entire point of the homework, it was for you to figure out, every single bug you could make, starting with, hey, I can't get on AWS, and I've got data, now what do I do with it, right? I mean, we had that question too. So to all the way to the end, you actually manage to get something up and going, and you get decent performance out of it. And there's a certain learning curve. There's also a joy to getting the correct, proper results, right? And everything that you've learned in this homework will apply almost directly to homework 2, which is out, and then some. So you're going to have to learn a few more tricks in homework 2, which means there's a whole new collection of bugs, an entire new set of mistakes that you can make, and a new dictionary of complaints that you can post on Piazza, right? Anyway, so let me continue with the class. But before that, any questions? Did you guys have any questions about the homework? Homework 1 on the streams? No? None. Okay. All right. So let me continue with today's class. We are 1 lecture behind. This was supposed to be done last week. We're talking about convolutional neural networks. Now, before we begin speaking about convolutional neural networks, the story so far, we found that multi-layer perceptrons are universal function approximators, and they can be trained through variants of gradient descent. And you've gone through the pain of homework 1. You know exactly everything that must be done, or at least most of what can be done, right? The basic model we employed was something like this. You had a multi-layer perceptron. Some input went in. It gave you a class, a probability distribution over classes more precisely. And early on, we made an important observation, namely that when you have many levels in your network, the lower levels learn lower level features. The higher levels begin to combine these features into more complex patterns. So for this example, all of the neurons in the lower level learned each of these linear classifiers. The next level combined them into the little polygons, and the next level combine the polygons into the figure that you want. So you're really building up whatever you want hierarchically. So, and what were each of the individual neurons capturing? If I just assume that I'm using a threshold function as my activation, then the individual neuron was comparing the inner product of the weights and the input to a threshold. And if the inner product exceeded a threshold, the threshold had fired, otherwise it didn't. But then let's take a closer look at this. We've seen this before. So what we are really saying is that the inner product between x and w must exceed a threshold t. But vector-wise, when I speak of an inner product between two vectors, what am I really speaking of? The inner product between two vectors is effectively proportional to the cosine of the angle between the vectors. In fact, if both vectors are exactly the same length, the inner product is within a scaling constant of the cosine. Now, here's an outrageous statement. When I go into high dimensional spaces, pretty much all of your vectors are the same length. Now, it seems odd that I must say so, but think about this. As you go into higher and higher dimensional spaces, more and more of the mass for any upper bound on the length of your vectors, more and more of the mass is going to be concentrated close to the surface of the sphere. So when you get to really high dimensional spaces, essentially the entire mass lies on the surface of the sphere, which means they're all vectors are more or less the same length, which in turn means that when I'm looking at the inner product between two vectors, I'm really looking just at the cosine of the angle between these two vectors, right? And so when I say that the inner product must exceed a threshold, what I'm really saying is that the two vectors must be very close together in angle. The cosine must be greater than a threshold. So if the w vector were the red vector over there, what the perceptron is really doing is firing anytime the input lies within the cone, immediate cone, around the vector, right? But here's a different way of looking at it. The inner product is really just a correlation. This term is a correlation between the weights vector and the input vector. So the neuron is going to fire if the inner product, if this correlation exceeds a threshold, and it's not going to fire if the correlation does not exceed the threshold. So if this were the pattern of weights, this input has a very low correlation with the pattern of weights. So if a perceptron were provided this input, it's not going to fire. If it's provided this input, which looks very correlated with the weights, it's going to fire. So the weights literally represent the pattern that you're trying to capture, right? So when you speak of building things hierarchically, suppose I were to build a network which looks at these old little pixel displays, which some of you probably have on your watches or your calculators from many, many years ago, ancient stuff. If I gave you an arbitrary pattern of pixels, how do you decide if this is a digit or not? Now, if you were to build an MLP for this, presumably the first layer perceptrons would capture all the essential components of digits. So the weight patterns are going to be, as shown in the figure, the weights are going to have the same shape, can be arranged in the same shape as the input. And the next is simply going to see whether the right combination of these inputs happens, which means you would expect that the perceptrons of the next layer to actually capture the individual digits. If any of them fire, this is a digit, otherwise it's not. It's going to be more complex. You might actually also learn patterns that must not happen in digits and the first layer. But this is the base. But you get the idea. You're sort of starting from simple patterns and building more complex patterns that you're going to detect. This is what you would expect, and this behavior is something that we actually take advantage of. So, just to recap, MLPs are Boolean inputs. The perceptrons are correlation filters. You're going to checking the correlation between the weights and the input, and checking if that exceeds the threshold. And the layers in an MLP are detectors of increasingly complex patterns. So, you have low complexity patterns, higher complexity patterns, still higher complexity patterns, and finally the output. And the network is going to fire if the combination of detected basic features matches an acceptable pattern for the desired class of signal. Like, have I seen a nose and a mouth and eyes? Then this is a face, right? So this is the basic idea of how you expect a network of this kind to behave. Now let's go to a completely different problem, right? It's not completely different. We're going to build on those ideas, but the problem that we're going to start off with is slightly different. I want to build a network, a model, that can recognize if the word hello was or welcome was spoken. So I will take isolated recordings, which is to say, I'm going to pull up my recorder. I'm going to say welcome, and I have an instance of welcome. I can take many instances of these. I can build my own training set. I can build my network, and later, when I want to recognize whether welcome was said or not, then I can actually say welcome again, and the network must fire. Now, as we know from homework 1, we are not going to be representing the signal as just a bunch of sample values. We will represent it spectrographically. X-axis is time, y-axis is frequency. The color, the intensity of the picture tells you how much energy you have in any given frequency at that particular instant of time. Now, what's the most simple idea, a simple way of building a network? I can actually a classifier for this. I can just give this entire spectrogram as an input to my network and train an MLP, right? And I could do this. I can train this network over many training instances of the word hello. What is the problem with this setup? This is not really a really great thing to be doing. And the reason is this. Suppose I have an instance, a network that's really good at recognizing welcome when it's said that way. So the word welcome happens here. You have some pause in the beginning, a lot more pause later. Will that network also recognize this guy where the word welcome happens later in this recording? Will it? Anyone? You must have an answer, right? So would you expect the network that recognizes the first welcome to recognize the second one as well? Why not? So basically, if you think about it, if I simplify the whole thing, I have a black pen in the box, right? Just to make sure that people can see what I'm writing. If you simplify the entire thing, and let's just say I'm looking at just one component, in one case, you're going to see a vector of this kind, assuming everything is either 0 or 1. In the other case, you're going to see a vector of this kind. They're entirely different components. They are completely different vectors, right? So which means that something that recognizes the first guy is not going to recognize the second guy. I could make it recognize the second one if, during the process of training, I gave it loads of data with welcome occurring in every single position. The corresponding network is going to be very complex, right? So what we really need is a simple network that will fire regardless of the location of the word welcome and this recording. And we want it to be simple. So that we have an equivalent with images. So here are a bunch of pictures of what might be flowers. Do you see pictures which don't have flowers? Several of them, right? Anyway, so is there a flower in these images? Here's a classifier. This is exactly the same as the welcome, right? Does this recording have the word welcome? I can ask you a different question. Is there a flower in these images? And you have the same problem. I can take lots of pictures of this kind. I can train my network to detect flowers. The problem is a network that detects a flower in the image to the top left is not going to detect the flower in the network to the bottom right. For the same reason, those two images are completely different when you think of them as vectors in some vector space, right? So once again, we also need we have the same problem. We need a network that will fire regardless of the presence of the precise location of the target object that you're going to try to recognize, right? So this is a common situation where the location of the pattern is not important, the presence of the pattern is important. And conventional MLPs are very sensitive to the location of the pattern, because if I shift things by just one bit, you're going to a completely different position in the vector space, right? If I just move this bit from here to here, I'm ending up in a different orthint. This one from that position to the next one, I'm ending up in a completely different orthint of the input space, right? So Same thing with the voice, same situation. So how can we deal with this? Let's go back. Instead of trying to build a recognizer that's going to look at the entire recording and tell me if there is a word, if the word where hello has happened in this or not, what I can do is to build an MLP which looks at a much smaller segment of a recording, the size that I expect the word welcome to be, right? And this I can train to recognize the word welcome. And now I can scan this input all the way to the end. And once I've scanned it, what would I expect? If the word welcome has happened in one of these locations, or one or more of these locations, if the person said welcome more than once, I expect the network to fire, right? So if the question I'm answering really is, has the word welcome happened over here, then what I will be doing is just looking at all of their outputs. I can take a max, and if the max is greater than whatever by threshold, I'm assured that at least one of these guys in one of these locations I have found the word welcome, right? So now thing is, things are not very clean, right? When I say the word welcome, it's not going to be in precisely one location. If I move over by 10 milliseconds, I still expect to see the word welcome. It's not that bad. So instead of just looking at a max, I can actually do something slightly more complex. I can make a perceptron which says, if I see the word welcome in 3 consecutive windows, I'm going to recognize, say the word welcome has happened. If I see it in exactly one window, I don't see it in others, then that's probably a misfire due to some noise pattern, right? And I can even make that even more complex. I can actually put an entire MLP on top of that, just to sort of affirm the same logic that I just mentioned. So this entire network, now observe, what I have really done is to scan the input with a multi-layer perceptron which recognizes the word welcome. But this entire thing, where I have this network scanning the input at each location and all of their outputs going into a final MLP, that too is just one giant network when I draw it like this, right? It has many subnets. The only difference between a conventional network and this guy is that each subnet is identical to every other subnet, right? Same thing I can do with images. I can build a little flower detector which looks at some small location of the image, and it can tell you, this is an MLP, this is a conventional MLP. So again, we are scanning the image with a conventional MLP. This is something I want to burn into your head when I'm speaking of these models, okay? We are not doing anything magical. We just took everything that we learned in the previous classes, everything that you implemented in your homework 1, but we're using that model to scan and input for patterns, okay? So here, I could be scanning this guy and looking for flowers. And eventually, I'm going to scan the entire image. At each location, I'm passing that entire block through a multi-layer perceptron, which produces an output. So I'm going to get an output for every position. And then finally, I can either do a max or put it through an MLP. Same logic as in the case of when I'm scanning an audio recording for the word welcome, right? And this too is just one giant network, with the only difference being this giant network is composed of many subnets which are all identical. Each subnet is looking at some small portion of the input, right? So these in both cases are really just large networks. Now suppose I want to, now where did I actually begin? I said I'm going to build a detector for the word welcome and I'm going to scan. I'm going to build a detector for a flower and then I'm going to scan, right? This presumes that I've initially given you some training examples of the word welcome sliced out, flowers sliced out, from which you could train a network. That is not required. Why? Because this entire thing is just one giant network, right? I could give you many collections of flowers, images with flowers in different locations, and tell you whether it has a flower or not. And I could just use backprop to train these things, straight up. Nothing really changes, right? This is an instance of what we will call learning with weak labels. Learning with standard problem and learning with weak labels is that instead of giving you training instances, here's a flower, here's something that's not a flower, here's another flower, here's not a flower, here's something that's not a flower. What I will give you is a little collection of images and say, in this collection, there may be one or more flowers. In this other collection, there may be one or more flowers. Here's a third collection of pictures where one or more are flowers. And then here are all these other collections where I can assure you that none of these collections have flowers, right? Now, this is a much weaker instance of labeling because you're not saying this is a flower, you're saying this bag of images has a flower in it, and you're supposed to learn to recognize flowers. That's exactly the same scenario you have over here. Each picture is really a bag of instances, each instance being one patch. Some of these patches are flowers, the rest are not, in the positive instances. And you're going to be training back these networks using backprop. Now, training a network using backprop is fairly straightforward. The only thing you have to keep track of is that all of these networks are identical. They're all clones of one another, which means that if during training I modify the parameters of this subnetwork, I have to mirror that modification in every copy of that network, right? Same thing here. If I modify this guy, I have to mirror that in every copy of that network. So these are what are called networks with shared parameters. They're shared because you are enforcing this restriction from outside that this parameter over here is going to be the same as this other guy here. So here, for instance, and there are many ways of sharing parameters. So here, for instance, I can say that I have this network, but I'm imposing the constraint that this weight is exactly the same as this weight. It's a constraint I'm imposing from the outside, right? Now, once I do so, what I'm really saying is that this weight, the weight between the ith unit of the kth layer and the jth unit of the k plus 1th layer is the same as the weight between, say, the mth unit of the lth layer and the nth unit of the l plus 1th layer. I can impose these sharing these restrictions on sharing in any arbitrary way, right? And both of them are going to be identical to some value ws, where s represents the set of weights which are being constrained to have the same value. So, if during learning, I perturb this value a little bit, that means I'm going to be perturbing both of these guys the same way, right? So here's how you think about it. How does this actually modify backpropagation or the training procedure? So here's the influence diagram. I know that both of those weights have the same common value. So if I modify this value, that's going to modify this guy, that will modify the divergence that I'm going to obtain for any training instance, right? If I modify this one, it's also going to be modifying this other weight, which too will modify the divergence that I'm going to get for any training instance. So if I want to find the derivative of the divergence with respect to this little parameter, I'm going to be having to add I'm going to have to add the contributions of both paths in this influence diagram, which means the derivative of the divergence with respect to this term times the derivative of this guy with respect to this common weight, plus the derivative of the divergence with respect to this term times the derivative of this with respect to this guy. These derivatives are just 1 because you're saying ws is the same as this weight, right? So that's simply going to be the sum of the derivatives of the divergence with respect to these two individual components. So, and this term over here is what you would be computing using backpropagation. These two terms are what you'll be computing using backpropagation. But once you've figured this out, now you can actually train this network, right? All that means is that if I say, let's say all of those edges painted red are constrained to have the same value, then the derivative of the divergence with respect to that value is going to be the sum of the derivative of the divergence with respect to the weights for each of these edges, right? And which you compute using backprop. And then you can just, yes.
Why are we having the shape parameters? Is it to reduce the computation power, or does it give any other advantage?
Tell me, where did the shared parameters come from? We just went through this whole discussion for a few minutes, right? We are scanning the image. So if you're scanning the image, the networks are the same, right?
I think this is only scale invariant, but not shift invariant, but not scale invariant.
You could make it scale invariant, in which case you're going to have a slightly more. So anything that you do with shift invariance can be done with transform, scale. You can introduce any kind of invariance, and each of those ends up being a different variant on the same basic network, right? So anyway, so if I were to modify backprop for shared parameter networks, and these are not the only kind of shared parameter networks, we'll see them again in other networks as well. This is your standard backprop. You'd be computing the derivative of the error with respect to each of the weights and updating the weights individually. When you share parameters, things are going to be slightly different. Let's say I have a set of weights which share the same value. Then I'm going to be computing the gradient of the error with respect to the weight for the set by summing this summing the derivative of the divergence with respect to every weight in the set, and then are using that to update my to perform the gradient descent update. So nothing really changed, right? And that one little term is going to be computed using backprop. So story so far, we have position invariant. If I want position invariant pattern classification, I can perform this by scanning. 1D scanning for sound, 2D scanning for images. I can have 3-dimensional data or higher dimensional data in which I'd be scanning in many dimensions. All of these result in just one giant network where the network parameters are being shared, right? So, and you can just use the back propagation rules for shared parameter networks in this case. But then now, let's take a somewhat closer look. So what did I do when I first explained this? I started off with a network, a multi-layer perceptron, and I scanned the entire picture using the complete multi-layer perceptron. Instead of doing it like so, let me focus on what happens with one of these units. Okay, so let's say, so I've just gotten rid of the input layer. The input layer is just the image. Okay, yes.
A couple of questions.
Mm-hmm.
Firstly, you motivated the window by talking about how the window can be used to, the size of the window can be used to encompass an object, right?
Yes.
In this case, probably the window is big enough to take to encompass the whole flower. But let's say we have a softmax and we're basically trying to find the probability of different objects. Does that mean we have windows of different sizes, or like how does it work? What if I have another object which is bigger?
You're conflating multiple things here, right? So focus for now on having just one single object, and we'll see. You know, we need a certain variance in this as well. Don't really want to be the size of the window either, right? And these things kind of work out. So I'm just sort of motivating the whole idea to see how these things, you know, how the whole model can be built up. But hopefully the answer to your question comes in a few minutes. Okay.
And the second question was, so we are basically telling, during a back propagation, we're telling our algorithm whether or not a flower exists.
Yes.
Right? So if one of the windows is, let's say, the bottom right corner, and there clearly is no flower there, it's just the sky, we're still telling it that there's flowers somewhere in the image. So how is it supposed to know that this part of the picture does not have a flower?
It doesn't, right? So this is all you're saying is that somewhere in this image, imagine I just pick a max, right? Then hopefully your back propagation is going to be propagating information only to to the specific subnets where the flower actually lies, and the rest of them are going to be switched off in the forward pass through the network. So we don't explicitly have to say where the information is. Anytime you sort of, I mean, maybe we'll see this in a little bit too. You had a question?
Yeah. So the way that I used to think about this was that each part of the image was just a different input to the same network, as opposed to having multiple networks for each part of the image. Is that one and the same, or is that so? Like you're talking about each small part of the image has its own network with shared parameters, versus just having one single network where the input is the shifted parts of the image.
They're exactly the same as it is exactly what I'm telling you.
Okay.
So to answer your question, right?
If
I'm sort of stepping one step ahead, but let's say I have many inputs over here, let's assume that I'm using a max at the output, right? I'm using a max. And let's assume that the difference between all of these is considerable, right? And let's assume that this guy is the maximum. Then what does the derivative really compute? The derivative says if I vary this value a tiny bit, how much does the output vary? Correct? So if I vary these guys a tiny bit, the output is not going to vary. So when you pass the derivative back, these derivatives are going to be 0. And the only direction in which the derivative is going to go backwards is the maximum value, where changing the value a little bit is going to change the output. So you naturally end up updating only those portions of the network from where the information actually is being derived. Okay? So now let's go back and take a look at something answering your question, right? So consider a single neuron in my network. What is the work this neuron is performing? At each position, it's taking a weighted combination of all the pixels that it's looking at, applying some activation to it, and producing an output. And then it goes to the next position, does the same thing, and the next position does the same thing, next position does the same thing. Each neuron is individually scanning the image. Correct? And so I can reorder the manner in which I'm performing my computation. Instead of scanning the entire image using a multi-layer perceptron, I can now scan the image using the individual neurons like so. Each of them is going to produce a map, right? And then I can, to decide whether there's a flower in that specific location, I just have to pick up the outputs of the individual neurons when they were looking at that particular location, combine them downstream, and I'm going to get the rest of my classification. Nothing really changed. I'm performing the same operation. The only thing that changed is the order in which I was performing the processing, right? And this is basically what you're talking about. This is just a change of order in which the processing is being performed. I can recurse the logic. I can now do the same thing for the next guy. If you look at what that first neuron is producing in the second layer, that's looking at these outputs combined, meaning the outputs of each of the neurons in the first layer when it's looking at the top left block. And then if I move one step forward, it's producing an output, it's producing whatever output it would have if the entire network were just looking at the shifted block. And so I can literally scan the entire image in exactly the same manner using the neurons in the second layer, right? And now, if I want to decide whether there's a flower in this box or not, all I have to do is to see what is the output of these neurons when I was scanning that location. The output of these neurons when I was scanning that location is going to have been derived from the highlighted yellow pixels over here in the first layer, right? And then I can just pass that through the rest of the network to decide if there's a flower there or not. Correct? And the final neuron, that too could be doing the same thing, right? I can basically recurse the same logic. So basically what has happened over here, I haven't changed what I really did. I'm still scanning the image with a multi-layer perceptron. Except that instead of scanning the image with a complete network, I'm scanning it one perceptron at a time. I've got to scan it initially with all the perceptrons in the first layer. Then I've got to be looking at the combined outputs of the perceptrons in the first layer and scan those with the perceptrons in the second layer. Then I'm going to have to look at the combined outputs of the perceptrons in the second layer and then scan those with the perceptrons in the third layer, and so on, right? So those of you who went through the CNN recitation and who are going to be looking at the CNN homeworks, observe over here that this neuron this guy is actually looking at 4 maps, right? In this example, it's looking at a stack of maps produced by every single neuron in the first layer. Whereas in the first layer, each neuron was just looking at the picture, right? A single picture, or whatever, or if you had a stack of pictures, you'd have a stack of, many of these. But then once you go to the next layer, you're looking at the combination of outputs of all of the neurons in the first layer, right? And this goes on. And so now this is beginning to look familiar, isn't it? This is what we called our convolutional neural network. It's not quite it yet, but the basic idea is still the same, that a convolutional neural network is nothing more than scanning an image for a pattern using a traditional multi-layer perceptron, and this results in a shared parameter network. And this shared parameter network is going to be position and shift invariant, which just throwing the entire image at a network, a characteristic that just throwing the entire image at a network wouldn't give you, right? And so now to detect a picture at any location in the original image, I just have to look at the output of the final perceptron when it's looking at that specific location. Or if the problem is there a flower in this image, I can just pass that entire collection into a final perceptron, which could be a max or a full multi-layer perceptron, and decide. And the reason again that you would want an MLP is that you expect that a small shift shouldn't suddenly lose the flower, right? In fact, more to the point, a small shift should still find you a flower. If it doesn't, you're probably finding noise. And so that's what the final MLP is actually going to be catching. Questions? So I'm just redrawing the final layer, what we call flattening it in the standard terminology, and then you're going to pass that through an MLP. Now, let's go back to where we began the class from. We started off saying, falling asleep. So we started off saying that when you train an MLP properly, an MLP that's doing its job properly is going to be building its patterns hierarchically, right? The lowermost neurons are going to be to capture the simplest features. The next level neurons are going to capture more complex features, and so on. I'm sorry, I'm just amused. Right. So it's worse still when I fall asleep when I'm here, right? It happens sometimes. Anyway, morning classes, afternoon classes, every class is the same thing. Anyway, and we saw this in this example as well. Now we'd like to embody the structure explicitly into our network. And how can we do so? Now let's go back over here. The entire MLP looks for a flower-like pattern, but then something interesting is happening over here. I've not distributed the representation. What has happened is that each perceptron in the first layer is looking at the entire block. This is an answer to your question, right? Each perceptron is looking at the entire block to decide if it has a flower or not, right? And so each of these guys is going to be looking at the entire block, and the subsequent neurons are looking at the outputs of the first layer. So if you look at what that neuron is looking at, the one in yellow in the top, at the top left corner of the patch in the middle, that neuron is looking at the entire block, because it's looking at the outputs of neurons in the previous layer, which are also looking at the entire block. Now, the condition I really want to satisfy is that I want that guy in the central block to be looking at in the central patch to be looking at the entire block. It's not necessary for the guys in the first layer to also be looking at the entire block, right? Which means I can distribute my representation. How so? I can say that the first layer perceptrons are going to be looking at smaller patches, right? And so the first layer perceptrons are going to be scanning like so in this manner, right? And the next guy can look at that block in the output of the first layer, right? And it too is looking effective, and it's still effectively looking at the entire same, the big patch in the network, right? Yes.
In that final output, where there is a flower, there will be more activations of that.
That's what you expect.
Then still we are looking at a single position, right? We didn't come out of the position. In final map, we'll be having where the flower is, their activations.
I'm not sure I completely understood your question.
But the objective is that, you know, each of the pixels in the map at the output of the final layer gives you information about one location in the image. And we're going to be looking across all of them to decide if there is a flower in the image or not.
Okay.
Right, so maybe your question really is your answer, right? No?
Yeah, I got it.
Yeah, so, okay. Now,
what is there on the slides, what I'm not talking about here, is this is still exactly the same situation that we had earlier. This is still a shared parameter network, okay? But then the way to look about it is that it's a shared parameter network starting from this position, but within each network, this guy is no longer a pixel, a single perceptron. It's a little multi-layer perceptron all by itself, and that multi-layer perceptron too hierarchically is a shared parameter network. So the whole thing is just one giant shared parameter network. I won't go over the boring details of this because I'll put you to sleep even more than you are right now. But I've drawn the colors in the slides, and hopefully you can actually go over them and it happens. The point I'm trying to make is that at the end of it all, I'm still scanning the image with a multi-layer perceptron. The only thing that I'm doing is changing the order in which I'm performing the operations. And so if you know all about MLPs, you know how this works. Now, so what is happening when I do something of this kind? What is the advantage of distributing my scan in this manner? The higher layer implicitly learns the arrangement of sub-patterns within the patterns represented in the lower layer. So you might, for example, find that this guy fires if the first perceptron fires in the top left location. The second perceptron fires in the second location over there, shown in red. The third one fires if the central, the central location, and the fourth one fires here. So if this particular combination happens, maybe that guy highlights up, right? So what are we actually learning? We are learning that we should be looking specifically for patterns of this kind, where whatever sub-pattern the first guy is looking for must happen in the top left corner. Whatever sub-pattern the second perceptron in the first layer is looking at must occur immediately to its right. Whatever sub-pattern the third perceptron in the first layer is looking at must happen in the middle, and so on. So you can actually learn more complex structures in this manner, and the structures themselves are, can be scanned for and can be shared across different blocks. Now I can recurse this whole logic, right? Why stop at 2 layers? So I can say that the first guy is scanning like so, really small. The second guy is looking at small subgroups of outputs of the first layer, and which means the second one is looking at this block here, right? And the third guy could be looking at 4 pixels from the second block, and effectively what's happening over here? The actual block is now being looked at all the way by the guy at the end, right? And the same thing. So all we've done is we've sort of started off with our basic model and distributed the representation over many, many layers. But this still remains the individual blocks are themselves. Each of these guys are now themselves shared parameter networks whose, sub-networks are shared parameter networks, whose sub-networks are shared parameter networks. But the entire thing is still just one giant MLP, right? Which is equivalent to scanning the image with an MLP. So, questions? Piazza? None. Okay. So why distribute? There are a couple of different reasons. We are able to look for small sub-patterns, right? Now looking for small sub-patterns is it actually going to be necessary? It's the same. We're basically recursing the same logic that we had earlier. Instead of providing lots and lots of examples of images with flowers everywhere and training one giant network, we took advantage of the fact that a flower is a flower, and you can just scan for a flower, right? But then you're recursing the logic backwards. You're saying that a petal is a petal, I can scan for a petal. And so you can have a shared parameter network for petals. And then I can go one step back and say parts of petals that look very similar across different kinds of petals. So then you can scan for those. And so you're using commonality of structure to simplify the structure of the network itself, which means A, you're going to need a lot less data to be training it. There's a lot less variety of input that you have to provide it for it to learn, right? You would expect, for instance, that a network that learns to scan is going to be able to fire if there are flowers at the bottom right corner, even if during training you only provided it with pictures in other locations, right? Not strictly so, but you would expect to see some behavior of that kind. So you're able to communicate information from one portion of the input to the other. There's a second more important aspect to it, which has to do with the actual number of parameters. So there's a generalizability in the model itself, but there's also the business of the actual number of parameters. So let's say I have my image. So forget about the entire image. Consider a single block. So let's say my single block is k cross k, but then my first layer neurons are looking at smaller blocks of size L cross L, right? Now, if I were just looking at the entire block of k cross k, then if this were k cross k, and if this entire block were going into a perceptron, I'm going to need k squared weights, right? On the other hand, if I'm scanning this guy per perceptron, right? Per perceptron. Now, if on the other hand I'm scanning this guy like so, with blocks of size L cross L, I'm just going to need L squared parameters over here. But then obviously, in order to compensate for it, I'm going to be looking for multiple patterns. So now I would have multiple perceptrons in this layer, and they are going to go feed into a second layer perceptron, right? So in the one case, I had just a single perceptron looking over the entire block. In the second case, I had, say, n1 perceptrons over here, which are feeding into another perceptron here. So the total number of parameters is going to be L squared n1 plus whatever is feeding to the next layer, right? So the comparison is going to be between k squared and L squared n1. Make sense to you, right? And I can keep recursing this logic, right? So if I have this distributed over multiple multiple layers in this manner, the first layer is going to look at L squared n1 parameters per perceptron, right? The second one is going to look at L2 squared times n1 times n2, because now we are looking at across entire groups of neurons, right? And so as you go down, for each layer, you're going to see, for the first layer, you're going to see L squared. The first layer is going to see L squared n1 perceptrons. The second layer, L prime squared n1, n2 parameters. So why the n1, n2? Because in the second layer, you have all of these n1. You are looking at many maps simultaneously, correct? You're looking at n1 of those, and all of those are feeding into each perceptron. And the third layer is going to be, say, L double prime squared n2, n3. The total number of perceptrons, total number of weights is going to be the sum of the lot. And the final layer has an interesting characteristic. You have to make sure that the patches by themselves eventually scan the entire block. So it's k divided by the product of all of the L's in the previous layer, right? So this is the total number of parameters that you would need if you're using a shared parameter network, if you're actually distributing the representation over many layers. And let's look at some numbers over here. So here I have a simple example where I have a block of size 16. I have 4 perceptrons in the first layer, 2 in the second, and the final one is just one layer. if I don't have the distributed representation, if these blocks, if the first layer perceptrons are looking at the entire block, then the total number of parameters that require, weights that require is about 1034. If on the other hand, I decompose it and say that each of them is looking at a block of 4 cross 4 and share it across multiple layers, I end up requiring only of the order of 160 parameters. So there's an entire order of magnitude reduction in the size, in the number of parameters, just because I distributed the representation across many layers. And as the input gets larger, as the number of layers keeps increasing, you'll find that this gap, the difference between the two, increases very fast. So it's also a matter of how many parameters that you have to train, right? So, skip that. So distribution forces localized patterns in lower layers, which is more generalizable. And the distribution also helps you reduce the number of parameters required to represent the entire input space. In all of these, the key intuition remains that regardless of how you distribute the representation across different layers, what you are really still performing is scanning the input with a simple multi-layer perceptron. The only thing that happened with the distribution was that you shared parameters more and more, right? And when I call it a convolutional network, all I did was take this business of scanning a network with a multi-layer perceptron and reorder the manner in which I perform the computation, and look at it perceptron by perceptron as opposed to block by block, right? The only thing that happened was a change of the order in which the computations were being performed. Okay, so here's a slightly different perspective to the same idea. I can the entire operation can be redrawn as before as maps of the entire image, which is basically what you traditionally hear when you're reading about convolutional neural networks. That the first layer filters is what we call them, right? Scan the input and produce maps. Then the second layer, filters scan the maps produced by the first layer jointly and produce more maps. And the location at any one point must be looked at simultaneously to decide if there's if the target object occurs there or not. But it's basically the same idea. Now this is one simple way of looking at it, but really a much more intuitive and much more correct way of looking at it is that you're scanning for an image, scanning using a classifier, right? And the scanning, if you think of it as scanning with a classifier, then you actually end up with more intuitions that help us downstream. And this business of scanning with a classifier also leads to things that you mentioned. I can say that I'm going to rotate my perceptron weight patterns a little bit, and you can get a rotation invariant representation, or I can scale them up, get a scale invariant representation, and so on. Anyway, so the patterns in the input image that each filter sees. Now we use the standard terminology. We're going to call these perceptrons filters. These are filters which are scanning for patterns, right? So again, remember that the patterns that each filter looks for is basically the pattern of weights for the corresponding perceptron, right? So the pattern in the input image that each filter sees is what we will call its receptive field. Now in the case of the perceptrons, the filters in the first layer, the receptive field is simply going to be the arrangement of the weights itself. What about the second layer? The second layer is looking over combinations of patterns from the first layer. So it's really hard to determine what the receptive field of a perceptron of a filter in the second layer is going to be. There are ways of actually trying to guess it, but it's not simple. And although I'm using examples like flowers, petals, inflorescence, and so on, when you actually learn these things automatically from data, they may not even begin to make sense, right? It's up to human interpretation. Now, again, the final layer can feed directly into an MLP, and even if you go with this perspective, this is exactly the same as a shared parameter network we begin with. Now, let's add a little bit of let's add a little to the actual processing that we've been performing so far. Now, I would like to also account for the fact that you may have some jitter in the first level patterns, right? So remember, one of the things I mentioned is that maybe the so the first level perceptrons might be looking at something like this, right? So I have multiple filters and they're looking at different guys, and maybe the next one decides that this must fire here, this must fire here, this must fire here, and this must fire here for this guy to fire, right? If we learn something of this kind, now does it really have to be such a hard and fast rule? If this first pattern, just locally, instead of occurring here, were to occur slightly shifted, I'm apologizing for people who can't see the red on the screen, but suppose it were to happen like so. Must the perceptron simply fail, give up, saying, no, it didn't occur exactly where it was supposed to happen? That doesn't make sense. You expect in natural data to find small amounts of jitter, right? And you naturally want to be able to account for little bits of jitter in the patterns that you see, so long as they combine in the appropriate manner. And so here's what we can do. What we can do is we can decide upon a tolerance that if this particular pattern that I'm looking for here were to occur anywhere in this block, I will say it has happened. If I decide upon a tolerance for how much the thing can move around, then remember, I'm looking, this is the same as the original problem we mentioned, right? Is there a flower in the image? We scanned the entire image, we took a max, right? We could perform the same operation over here and say, I'm going to look at all the blocks in the small region, and if this low-level pattern has occurred anywhere in the small region, I'm going to fire. So which would mean that one could just look at that small block over there and find out if any of them have fired, which is to say take the maximum value and just copy that over, which is simply detecting that the pattern has occurred within limits of positional tolerance, right? And so and the max literally is going to be, so you can think of this max operation also scanning the image. Once you got the outputs of the first layer, the max operation can be scanning the image, and you'd get a scanned image over here. The max operation is going to look something like this. You have 4 values. You're just going to pick the largest value at each point. And if I think of now the max is also just a perceptron, a standard. It's not your traditional perceptron, but you can also think of it as a nonlinear combination of the inputs, right? So if these were the outputs of the 16 blocks, the max is going to be applied to each, to small combinations of each of these, and you get the next one, right? Yes.
Because the max is just a low pass filter.
Yes. A max is. It's not a linear operation, so you can't really call it a low pass or a high pass filter, right? It's an edge detector of sorts.
Sure. But you're smoothing.
It's smoothing.
You're blurring.
You're blurring. Yeah. So you're enhancing edges. You wouldn't even be blurring. The max is nonlinear. It's kind of hard to interpret. It's like a median filter. Yes. This is what I mentioned, right? We'll look at this later. But then if you go back over here, this is exactly what happened at the end of the network, right? We shouldn't get too hung up on the arithmetic. A lot of it has to do with, the logic behind it, the rationale. And what is the rationale of backpropagation? The rationale of differentiation is, say I have 4 inputs going into some unit, and I have an output. The question you're really asking is, how much does a small change of this guy change the output? That is the derivative, right? So suppose I have something like 7, 2, 1, 0, and this is a max. Will a small change of this guy change the output? No, so the derivative is 0, right? So long as the max is sufficiently separated, there's only one direction in which the derivative is going to travel. The rest of them are 0. So it's not really a problem. If the max is not well separated, then you do run into an issue, but it's highly unlikely to happen in most cases. And we take soft maxes for these. Won't get there. Right. So, questions? Okay, so you can think of the max as just, remember, I'm just redrawing my scanning as a standard multi-layer perceptron. Then the max is looking at the outputs of the first perceptron layer. I'm going to have a second layer of perceptrons, which is just looking at outputs over small blocks and picking the largest of those, but that's just another nonlinear combination operation. Nothing really changed. The max is not any magical block. It's another unit in your multi-layer perceptron, and you're still performing the same scanning operation, right? So again, you'll be scanning exactly the same as before, right? As we saw, and you're going to go from top left to bottom right. Now, this is where some of the engineering comes into the picture, right? Conceptually, all of this is fine. Conceptually, we figured we want to scan the image, that even if I'm scanning, I can think of the act of scanning puts me in a very nice position where I can learn from data where things have not been clearly demarcated. I no longer need to be told that there's a flower over here. There's a flower over here. I can just give it pictures saying these have flowers and these don't. So this business of scanning helped me do that. I can distribute my representation by having this network be hierarchical. I can allow for position invariance by dropping something like a max. All of this was conceptually nice and clean. But then eventually, where the rubber hits the road, you actually begin looking at engineering issues. So when I'm scanning, do I really need to scan looking at one pixel shifts? That's not necessary, right? If I jump by 2 pixels at a time, I can still expect to get more or less the same behavior. But what will happen? If I'm scanning 1 pixel at a time, the map that I get is going to be approximately the same size as the input. If I'm scanning 2 pixels, jumping 2 pixels at a time, the map is going to be shrunk by a factor of 2 along each dimension. And so if it were pictures I was scanning, the maps are going to shrink by a factor of 4. If I'm scanning 3-dimensional objects, the max is going to be, the map is going to shrink by a factor of 8 and so on. Again, there's nothing magical about pictures, nothing magical about audio signals. There's nothing magical about, this whole business of scanning for patterns can be extended to any number of dimensions. The idea remains the same, right? So, and how the whole thing works, if you sit down and intuit about it, you'll find it all works out in pretty much the same manner. The same thing with the max. When I'm jumping forward, if I'm permitting jitter, then I don't necessarily need to skip 1 pixel at a time. I could be jumping 2 pixels at a time. This is something that we normally always do. In the sense that if I find something over here, then that entire block is taken care of. I can actually jump to the next block. This is the logic behind it. And there's also a biological logic that we will look at in the next class. But the max can itself also have its stride, like so. And this results in a shrinkage of the map. And this whole operation is something that we will call pooling. And why we call it pooling is that you're looking at many little pixel values, and you're picking one of them, so you're pooling them in some manner, right? And when the stride is greater than 1, we're also going to call this downsampling. Now, here's something. When I talked about the entire picture, I said that I could use the max, but I also said we replace the max with other things. I replace the max with a perceptron, right? I replace the max with a multi-layer perceptron. This was learned behavior, right? So in the same way, this pooling operation doesn't really have to be a max. This can actually be learned behavior. Where the learned behavior is common, it's a common operation across all positions. So that can actually be either a perceptron or an entire multi-layer perceptron. This is what they would call network in network. But it's really a learned behavior for the pooling, which is translating the idea that we had at the end of, when you process the entire picture to local blocks in the network, right? Now, so here's how, if you're actually looking at non-overlapping strides, the behavior is going to be. The first layer is going to produce some maps. Then you sort of partition it into little non-overlapping blocks. You're going to pick the largest guy from each block. You'd get a shrunk map. Here's an example of how that happens, right? If I have a map which has 16 values, and I decide to look for positional if tolerance of 2 pixels in each direction. Yes.
Question from the stream. You're asking about the distinction between max pooling and max filtering, if there's a difference or not.
What's the difference between max pooling and max filtering? There really is none. We are calling that unit a filter. In the case of max filtering, the operation that's being performed is called pooling, but the terminology varies. It's the same thing.
Gotcha.
So, and then the higher layers can keep performing the same operation. The next layer is going to work on these max pooled or max filtered maps. Yes.
Is this primarily for parameter reduction, or does it have other benefits?
So this is primarily the actual pooling operation is for positional tolerance, right? The shrinkage of the map results in parameter reduction. So there are engineering aspects to it, but there's also the conceptual aspect is that you want it to be distortion invariant to within a certain limit. But if I begin jumping and if I begin having these so-called strides which are greater than 1, this results in a reduction in the size of the data, and so you have reduction in the number of parameters. Right? Yes.
So generally the pooling happens immediately after filtering, right?
Yeah.
So we can have filter pool.
There's also the activation, right?
Oh,
Yeah, so you're going to be scanning. You'll be putting it through a multilayer perceptron. You're going to get some outputs. Then you pick the largest. Yeah. But this is, I mean, all of this can be mixed
around when you actually begin implementing these. We'll see this in the next class. The amount of engineering that goes into these systems is huge. So whether they actually perform a max or not becomes, a decision to be taken too. Whether they're going to actually have strides, large strides, also ends up becoming a decision that must be taken, and so on. Now, so here are the names. The individual perceptrons at any scanning or convolutional layer are called filters. They filter the input to produce an output image. And the max operations are also called max pooling or max filters to answer the question on the string. And this entire structure is called a convolutive or a convolutional network, depending on who you ask. So we've basically built up the logic behind where this model arrived from. It wasn't just, dropped in from the sky. Well, I'm lying. It was actually dropped in from the sky. But there is a logic behind it, right? And where in the sky it was dropped in from, we will look in the next class. It has to do with many dead cats. It does. Now. So here's an example of a standard convolutional neural network. This was the first really successful instance of an application of a convolutional neural network. Was by Jan LeCun back in the early 90s, who showed you can recognize handwritten digits very accurately using these networks. And the US Postal Service actually ended up using this system. I don't know if they still do, but this was the USPS usage of convolutional neural networks to scan handwritten addresses was probably one of the first uses of neural networks in a really large-scale commercial deployment. So here was the, we'll see this figure again, but this just sort of gives you an idea of the scale of the operations that were performed back then. Now these things get much larger. We'll see in the next class. The input image in this case was something, 32 cross 32 pixels, which is, how much is that? 1024 pixels, right? He had 4, was it 5, first layer filters. And the filters were all size 5 cross 5. Now something interesting happens over here. If I'm scanning a 32 cross 32 image using a 5 cross 5 block filter, then at the boundaries, beyond some point, you're going to fall off, right? So whether you really want to permit falling off or not decides the size of the outcome. So here he did not. So as a result, these 32 cross 32 images end up becoming 28 cross 28 because the final 4 pixels cannot be used on either side, right? But then you have a max pooling by a factor of 2. These become 14 cross 14. And then he had 10 of these feature maps, which were all 2 cross 2. Oh, 5 cross 5, right? And also 5 cross 5. You end up with several 10 cross 10 images. Then you max pull them down, and the whole thing is just passed to a multi-layer perceptron to recognize digits. Now, if I do the same thing using one-dimensional convolution, we were talking about audio signals, and then I suddenly just dropped it and I began speaking of images, right? But if I let me go back and loop back all the, to the very first kind of data we mentioned. If I have a 1D scan of a spectrogram, now here observe that I'm not allowing scan in the vertical direction. I'm only scanning in the horizontal direction. This is what is called a time delay neural network. So the time delay neural network was probably the first real convolutional neural network that learned its features, that was proposed in the literature. This was Kevin Lang's PhD thesis here at CMU in the late 80s. So we have a lot of history in the entire neural network field. Now, the 1D convolutional scan, you're going to start off with a spectrogram, and then, so let's say I am trying to scan this image with this MLP, which is 4 cross 2 cross 1, then each of the 4 pixels, 4 perceptrons in the first layer is going to perform a scan, right? So each of them is going to give me one value at each position in the spectrogram. 4 of them are going to give me 4 of those guys. So although I've plotted them one on top of the other, each of those 4 really represents these 4, right? Then the next layer, if I have 2 perceptrons, each of them is going to be scanning some block from the outputs of the first layer perceptrons, like so. And each of them will produce 1 layer, right? So 2 of them are going to produce 2. Again, I'm stacking them one on top of the other. The whole thing is to show you that you're combining the outputs of multiple perceptrons in this manner to actually get an output. And then if I have a single final layer perceptron, that's just going to be scanning something like that. And then the whole thing can be passed down to a MLP or a max or a simple perceptron, what have you, right? This whole thing is a time delay neural network. And traditionally, when we performed time delay neural networks to recognize speech, we didn't actually use max pooling. The whole max pooling business, which allowed for jitter, was introduced for analyzing images. But in the case of audio, if you begin letting things jitter, they don't sound the same anymore. They actually sound scratchy. So you wouldn't actually allow for little bits of jitter in speech. So you don't have max pooling. So I maybe start ending early or late. I'm not really sure. But the story so far is we found that neural networks learn patterns in a hierarchical manner from simple to complex. And when we want to use these things to answer questions like, does this picture contain a cat? Or does this recording contain the word hello? Then this is best done by scanning, because this gives you positional invariance. And scanning can be viewed as classification with a large shared parameter network, right? Now, scanning an input with a network and combining the final outputs is equivalent to scanning the network with individual perceptrons, just changing the order of the operation and combining those and scanning again and so on, right? That's where the whole CNN structure came in from. So the first level neurons scan the input, the higher level neurons scan the maps produced by the first level neurons, and a final decision layer makes the final decision. And at each layer, we showed that a scan may be followed optionally by a max or some equivalent of it to account for deformation. For 2D or higher dimensional scans, the structure is what we'll call a convnet or convolutional network. For 1D scans, this is a time delay neural network. So I'll stop over here. Questions? Yes?
What would happen if you took the 1D, the image of the spectrogram, and treated it as a 2D image and did the scan it? Has someone done that? Tried that on respective?
So they do that. I mean, back when this was proposed, it was considered that it's not a very healthy thing to be doing. Lately, we are finding that there's theory and there's practice, and the two are not the same. So you can do all kinds of logically absurd and intuitively meaningless operations on these things, and the results keep improving. So yes, there are some conditions under which you can actually there's a rationale for looking for vertical scans. So the way this was represented, the vertical axis represents frequency, right? So the vertical axis represents frequency. The frequency is linear. Now let me give you a different representation where the vertical axis is log frequency. Right? And this is a common enough thing to be doing. So if I have my vertical axis is the log frequency, this is going to be, so let's consider two examples. This is frequency versus time, and this one here is log frequency versus time. Right? Now consider some fundamental frequency which varies like so. How will the harmonics change? The harmonics are going to be, instead of having it smooth, let me just show. So if this were like so, the harmonics are going to be of this kind, uniformly spaced, right? Here the harmonics are going to be spaced like that, correct? Here the harmonics are going to be, goes off. So as the fundamental frequency changes, the harmonics are going to be get spaced farther and farther apart. Now a perceptron, a filter which detects, if I'm playing a musical instrument, the timbre of the instrument is represented by the shape of the spectrum, the note is represented by the pitch, right? So I would expect that the spectral envelope over here is merely an expanded version of the spectral envelope out here. But a filter that detects this pattern is not going to detect this pattern because all the positions of the peaks have gone away, right? Now suppose I were using log frequency instead. If I were using log frequency instead, then what I would get is something like this because it's log frequency, right? And these patterns are going to be space log 2, log 3, log 4, and log 5 apart. But the entire shape, because now the a scaling of the shift simply becomes a vertical positional shift, right? Because the frequency axis is logarithmic. Now you can imagine that you can just use a single filter and scan vertically and detect the same pattern. Right. So depending on the nature of the representation, depending on the nature of the data, whether you really want to be scanning vertically or not, can change the outcome. But in the traditional PDNN, this was not done. Anyone else?
So not already understanding how backprops work with filters, because they're for maximum, you can kind of just ignore it, because it's not.
So wait, so do you understand how backprop would work if you didn't have max pooling?
Not really. So that's what I'm going to go like. How do you backprop like a filter? You mentioned
You don't backprop a filter.
You don't. How do you change?
No. So this is where things. Let me go all the way back, right? Although we are talking in terms of filters, I want you to think of this. This is exactly the same as filters. Correct? That come across? So we said that I could be scanning an image. Remember, we went through this whole business of saying I could be scanning this image with a network of this kind, right? And if I change the order, changing the order of operation gives you these maps, correct? But eventually what you're doing over the entire network is, over the entire image, is processing the network with one giant multi-layer perceptron, where each component, which has many sub-networks, all of which are identical, correct? But once I give you this network, for this backprop is straightforward, right? The only extra thing that we did was to say that this parameter, keep track of which parameters are identical. And then we shared the backprop over the list. We have the rules in that back here. So like that. So we have the shared backprop rules. In the next class, we'll actually go over this a little more detail, but the fact of the matter is that the shared parameter network the convolutional neural network is just a shared parameter network, and you can use this little shared parameter update tool to perform back, prop, and learn the parameters. Right? What you're doing here is identifying which parameters all have the same value, assigning them to the same set, and performing back, prop.
So when you change the way of so when you're changing the weights to backprop, are you kind of changing the numbers within the filter in a sense, or?
You're changing. So basically, when I change this guy is a filter, right? In the new terminology. So if I'm changing the weights of this perceptron, I'm effectively changing the filter.
Okay.
Right?
Yeah.
Every perceptron here is a filter. So one of the things I want you guys to stop thinking about is the traditional terminology that you've been taught. You know, because if you keep, if you stay with that, that's just one way of thinking. It's kind of useful to look at it from other perspectives. All right, thank you everybody. See you on Monday.